Okay, we're going to see how we would go about finding extreme values. So let's look at a graph with a closed interval from A to B, and let's look at the places where we have extrema. First of all, let's look for any absolute max. There's actually two different places that the function takes on the largest value when x equal q or x equal s. We see they're both absolute maxes, but they're also both local maxes because I can make an open interval that contains q so that for every x on this interval, the function values are less than or equal to f of q. In fact, less than in that particular case. And you can say the same thing is going to be true for an open interval about s. So let's look at the derivatives here, and we see that the derivatives equal 0 at both of those places where we have the absolute maximum. Let's look at r. At r we see that we have a local minimum because in an area around this is the lowest the function goes near here. We could make an open interval about r so that for every x in this interval the function value is always larger than or equal to the function value at r. So local min, looking at the derivative, it is 0 again. This is not an absolute minimum because the function goes lower, and in fact the absolute minimum occurs at p, and p, besides being an absolute minimum, is also a local minimum because we can make an open interval that contains p so that f of p is the smallest function value for x's in that interval. But the derivative is not 0 at p. In fact, the derivative does not exist at p because we have that cusp or corner. So we saw that the derivative was 0 or the derivative didn't exist for these places that had maxes and mins. We're going to look at Verma's theorem, which says if f has a local maximum or minimum at c and if the derivative exists, then the derivative is 0. There's a proof of Verma's theorem following this video, and please watch that. Okay, so let's see. Basically what this says is if the derivative exists at c and it's a local max or min, in this particular graph it's a local maximum, the derivative is 0. And you see that we do have a horizontal tangent there. The slopes of the secant lines are greater than 0 when we approach from the left, but the limit as we approach c of these secant slopes is 0. As we approach from the right, we see the slopes of the secant lines are negative, but the limit of the slopes as we approach c is also 0. So the derivative exists there, and it is 0. So let's look for absolute or local extrema. Let's figure out for this function where the derivative equals 0. So we're going to use a power rule, and then we're going to set it equal to 0, and we get x equals 0. So we could go, oh, okay, the derivative equals 0 at x equals 0, so that's going to be an absolute max or a min. Nope. The theorem says if the function has a local max or minimum at c and if the derivative exists, then the derivative equals 0. It does not say the reverse. It does not say if f prime of c equals 0, then it has a max or a min. So we got to make sure we use this in the correct order. In fact, as we look at this graph, the derivative equals 0 right here, but it is not a max or a min. Let's look at the absolute value function, and we see that we have an absolute and a local minimum when x equals 0, but the derivative does not exist there. So looking at Verma's theorem, it says if it has a local max or min and the derivative exists, it's 0, but the derivative doesn't exist there, so the theorem doesn't apply. You have to be careful when we're looking at the theorem because there are times that the derivative equals 0 but there's no max or min, and we can't just blanket say that if the derivative doesn't exist there's a max or min, because here's an example where the derivative doesn't exist and it's not a maximum or minimum. However, if it has a local max or a min, that's going to occur at a place where the derivative either equals 0 or the derivative doesn't exist. So we call these numbers critical numbers. A critical number of a function f is a number c in the domain of f such that either the derivative at c equals 0 or the derivative at c does not exist. This does not say that there's a maximum or minimum there, but if there is a max or minimum, it will occur at a critical number. So critical numbers are like the potential candidates for the maxes or mins. If there's going to be a max or a min, it's going to occur at these places, but just because the derivative 0 doesn't exist doesn't mean there is a max or a min. So let's find the critical numbers of this function. So we've got f prime of x equals, we got a product, first times the derivative of the second plus the second times the derivative of the first. And so this derivative is x plus 2x ln x. Now first of all, let's look at the domain of the function. We have this natural log of x here, and so we have to have x is greater than 0. So now looking at this derivative, if there's any places the derivative does not exist, well, for the domain of the function x is greater than 0, this is defined or exists everywhere there. So critical numbers are going to be places where this equals 0. Let's factor an x out. And let's set each factor equal to 0. We'd have x equals 0 or ln x equal negative 1/2. And then we'd exponentiate both sides and have x equal e to the negative 1/2. Okay, so our first one is x equals 0, but we got to throw that out because it's not in the domain. And our second critical number is x equals e to the negative 1/2, and that's actually our first critical number because the first one we had to throw out. So if we looked at a graph of this function, 1 over the square root of e is the same thing as e to the negative 1/2, and we see that the function at 1 over square root of e is negative 1 over 2e, and that ends up being a local and an absolute minimum. So it did occur at this critical number. If there is a max or a min, it's going to occur at a critical number. So our procedure for locating the absolute maxes or mins, we're going to have a function that is continuous on a closed interval. The extreme value theorem would apply then because we've met our two conditions of that the function is continuous on a closed interval, so we're guaranteed to have an absolute max or a min. So how we go about finding them is we're going to locate all critical points C that are on the open interval from a to b where the derivative is 0 or the derivative doesn't exist. So on this interval, find these critical numbers. These will be the candidates for the absolute maxes or mins. If there are maxes or mins, it's going to occur at those points or at the endpoints. So number 2, we're going to evaluate the function at the critical points and at the endpoints. Then going to compare these values, and the largest of these values will be the absolute maximum and the smallest of these values will be the absolute minimum.